Hello comrades, welcome to Electric Fields number 5. This one we're going to look at the Millikan oil drop experiment. It's not often that we actually look at historical experiments, but the Millikan oil drop experiment's a pretty famous one, and you sort of have to know a little bit about it to put some of their questions into context. So let's have a look at it. Just remembering what we have learnt before, that this is just a little summary of what we know already about electric fields, so you can pause that and have a quick read of it if you wish. And we've also been looking at these equations here, and these are all the units that we know, and we've also been introduced to these equations here, and we've been dealing with the force that charges experience between parallel plates. Now, an understanding of this is important for the Millikan oil drop experiment. So make sure you pause this and just have a quick read of it if you can. Now, who was Millikan? There he is, a famous physicist. Was born in 1864, obtained his doctorate in physics, and died in 1953. And this is his experiment. This is the actual equipment he used. It's a pressure vessel, and we'll learn out what the various parts were. There's a light, there's a microscope, there's the atomizer, and we'll see a few schematics of this shortly. That's the actual lab that he did this famous experiment in. So it's within modern history, and the basic schematics is what he did was he had two plates with a large voltage between them, so there was a strong electric field and there was also a uniform electric field. And in a chamber above he sprayed oil, and the oil droplets were allowed to free to fall under the influence of gravity. And there was a little hole in the top plate, and some of the droplets would fall through the plate and find themselves in this electric field. And the other thing he did was he ionized some of the droplets. Now the droplets contain millions and millions of oil molecules and gazillions of electrons, but by making some of the droplets gain or lose electrons, he could have them charged, and therefore they'd be charged droplets in an electric field. And he would then observe them through this microscope and their behavior. And through a very long process of observations and careful observations, he was able to discover some things that we'll learn about shortly. Another schematic here, just showing exactly the same thing in terms of the design. And this one's out of your textbook and shows a light source just to reflect off the droplets so that he could see them. Now, what was basically happening was, if you forget all the apparatus and you just think about the droplets within between the two plates, a droplet would have its weight force due to its mass, and if it was negatively charged, so it actually had gained some electrons, it would experience a force due to the electric field that was up. And what Millikan was trying to do was to balance these two forces and get the droplet to hover between the plates, and therefore he would know that the weight force is equal to the force due to the electric field. And so if the force due to the electric field is equal to the weight force is mass times gravity, and the force due to the electric field is the electric field strength times by the charge, he could rearrange this and have charge is equal to mass times gravity times the electric field. Now, if he knew the electric field and he knew gravity, he didn't know mass, but he could work out mass through a variety of ways. He could then work out the charge of the droplet. And you'll see on the OneNote there are two videos that you should watch relating to this, as to see what the actual droplets look like between the two plates. And now we're going to watch a video inside a video. Hopefully this works, and we'll see how we go. Let's hit play.
Between 1909 and 1916, Robert Millikan carried out experiments to measure this charge. Millikan's apparatus was simple. Two parallel metal plates with a uniform potential of 5,000 volts between them. Fine droplets of oil in a mist were allowed to fall between two charged plates. The droplets passed through X-rays and lose electrons, becoming charged. They pass through the hole in the top plate. The top plate was made positive so that the negatively charged drops were forced upwards. Each negatively charged droplet had just two forces acting on it: the gravitational force pulling it down and the electrical force pulling it up. When he balanced these two forces by changing the voltage, a droplet became suspended. As he knew the mass of the droplet, he worked out the size of the forces. Then he calculated the charge on the drop. He found that the charges were always multiples of an extremely small number. There were none in between. The smallest steps represented the size of the charge of a single electron. Because Thomson had found the ratio of charge to mass, Millikan could calculate the mass of the electron. The charge was indeed tiny. Electrons are all the same, each with the same charge and the same mass.
Hey, there you go. Hopefully you could hear that. I'll see if when I finish the recording, we'll see if that worked. So let's have a look at what some typical Millikan oil drop experiment questions are like. Here you're given the mass of the droplet and it's stationary, so it means that the two forces are balanced. You've got the distance between the plates, you've got the voltage across the plates, and you've got a value for G. And typically you would ask to calculate the strength of the electric field between the plates, the size of the charge on the droplet, and then how many elemental charges that means, i.e. how many electrons does that correspond to. That's the electrons that is gained or lost, not the total number of electrons. So first off, to get the strength of the electric field, E equals V on D, just put the numbers in, volts per meter. To get the size of the charge, Q equals mg on E. We've got E now, we can get the charge. And the number of elemental charges, so you take the total charge of the droplet and you divide it by the charge of an electron, and therefore this one has gained 4 electrons. Let's do another one, similar but different. Oh, actually, these are questions you have to do. So you'll find these in your workbook. That's question 2, question 18. Any tricks to these? No, they look pretty much standard. Just watch out for some traps. And that's alright. Okay, we've got that. It's a little bit different, but you should be able to do that one. And how many excess electrons? Yeah, that's pretty standard. And this one's just making sure that you understand which directions the forces are being applied, so you should be able to have a go at that one. Alright, so that ends that. Hopefully you can have a go at those questions, and if you have any questions, make sure you ask me and we'll make sure that you're clear. And the next video we're going to look at what happens to charged particles in electric fields and things called electron guns. Cheerio!